Our next speaker is Antoine Alaguero, talking about forming planets with air.
Yeah. Hi everyone. Thanks back for the introduction. Thanks for the invitation, and thanks to the organizer for this beautiful place, beautiful conference. My name is Antoine indeed. I'm from France, working in Grenoble as a postdoc. And today I'd like to introduce you to how to form planets with Phantom. So I will mainly talk on how to grow little dust grains into possible planets. And the schedule for today is, after a brief introduction, I will highlight the algorithm of how dust and dust growth evolve, proceed in Phantom. And then I will highlight the main results that have been obtained with this framework. And finally, I will highlight possible directions for the code in that regard. So let me first tell you a bit about planet formation, which all starts into a protoplanetary disk where you have tiny dust grains that are inherited from the solar medium. These dust grains, they are embedded in the gas disk, but they also collide with each other, and sometimes following these collisions, they push and stick, and so they grow to form larger aggregates that we call pebbles. And these pebbles also, by colliding one to the other, and also for some reasons that I will highlight later, they decouple from the gas and basically perturb the disk to form pebbles accumulation, leading to the formation of planetesimals that are basically kilometer-sized bodies. These planetesimals, a bit of the same story again, they collide, but they can also gravitationally accrete their surroundings, right? The small pebbles, also the gas, form protoplanets, and this planetary embryo will, through complex processes that I will not highlight, will form one of the exoplanets that we detect nowadays. There is also a way to bypass this short scenario, which we call the core accretion, which is disk instabilities, so also called gravitational instability, which is if your disk is massive enough, it can fragment and directly form giant planets, but I won't talk about this today. So you see here that in order to get this, you need the first row to happen. So let's focus on this, all right? And have a look at where the dust grains are located in the disk. So you see here a view edge-on of one disk, and basically you have dust everywhere, little dust grains everywhere. The biggest grains, they are located in the midplane of the disk. And this is because the dust wants to rotate at the Keplerian frequency around the central mass, but the dust, because of pressure forces, it orbits at a slightly lower velocity. And so the dust feels a constant headwind, making it losing angular momentum. And as a consequence of that loss of angular momentum, the dust will start to settle in the midplane of the disk, where it accumulates basically, and it is a promising environment for it to grow. That's why you have the bigger grains in the midplane. But at the same time, as this dust is growing as well and losing angular momentum, it also drifts towards the central mass. And so basically you also have accumulation of big dust grains in the inner disk. But that also tells you, because they drift, they lose angular momentum in such a rapid way that if you want to form planets, it has to happen quickly. You have to form planetesimals quickly, otherwise you will lose all the pebbles in your disk. And one of the ideas to do that is going through dust instability. You have one example here, which is called the streaming instability. It's basically an accumulation of dust being able to perturb the gas disk. The gas disk is being perturbed will perturb the dust, which will perturb the gas, etc., etc. And that will lead to clumping, basically, of your dust, which will gravitationally collapse and form planetesimals this way. All right, so why is dust growth important? Well, the main reason is that if there is no dust growth, you don't have planetesimals. You don't have planetesimals, you don't have planets. And if you don't have planets, you don't have planets. But dust growth also affects the temperature structure in the disk because it affects the opacity law of the dust, which also has dramatic impacts on the disk chemistry, but also on the chemistry at the grain shorter. Dust growth can explain the disk evolution through radial drift and vertical settling, and it is also key to understand multi-wavelength observation. For example, here of the same system, here in the infrared, you trace the tiny dust grains close to the disk surface, and here in the millimeter, you trace bigger grains that are located. This is able to explain this demography and the kind of substructures that we observe. And most important, when we have those kind of images, where we have a protoplanet that is observed forming inside an actual disk, well, we have to understand how it got there in the first place. So, kind of a big jump to go into the second part of this talk, but I'll start to highlight how dust works basically in phantom. And this depends on the coupling between the dust and the gas that we describe in what is called the Stokes number that you have at the top, which is a product of dynamical time and the stopping time. So this dynamical time can be, for example, the Keplerian frequency. And the stopping time is basically the time for a dust grain to be perfectly coupled to the gas flow. So if the dust grain is very small, you have very small stopping times. And the opposite way, the dust grain is big. So let's start with the most intuitive way to treat dust, which is called dust as particles. And it's basically, so you have your field of SPH particles, and you will just add another set of SPH particles to represent the dust. The sole difference with gas is that it doesn't have any pressure. So you involve these two populations of particles and you make them interact basically. And this is very good because it always works. But when your stopping time is going really low, if you have very small grains, basically you will need a very small time step in order to resolve that stopping time and the interaction between gas and dust. And so your simulations will end up by taking ages. So there is an alternative. When the grains are tightly coupled to the gas, you don't involve another set of SPH particle anymore. You just simulate the dust inside the SPH particle. It's called the dust as a mixture algorithm. And in this case, you evolve a common density, which is the sum of the dust and the gas density. And you also evolve in each SPH particle the dust fraction. And this way, you can't have directly the independent gas and dust velocity. You have a barycentric velocity of the gas and dust, and then knowing the interactions, you reconstruct the independent velocities. And so this is very fast compared to the other one, especially if you have small grains. But this becomes very wrong as well if your grains are decoupled from the gas, right? If you have your grains that wants to go basically another way from the gas, well, you clearly see that it won't go. Then let me talk to you about how dust growth is working. Now that we know a bit more about dust, let's make it grow. So it will involve a couple of assumptions. The first one being that it all happens inside the SPH particle, the SPH dust particle, and we'll assume that this particle represents an army of very small dust grains that have motions that we don't resolve, but we know that this motion, they make the grains colliding one with the other. And these grains, they have distribution in size, or I will talk in terms of mass, which is basically the same. And we'll just represent that distribution with one single value, which is, for example, the average. Or the peak, can be whatever you want. And then we will use the Stokes number once again. to compute the relative velocity of the tiny dust grains colliding. And this velocity depends on the stokes, but also on the gas turbulence. We will assume that gas turbulence is driving collisions between the dust grains. And we have like analytics for this unresolved turbulence that happens within this HPA particles. And so from that, we can compute the relative motions between our tiny dust grains. Once we know that, we will compare that relative velocity to a fragmentation threshold, which is basically depends on the grain properties. It's kind of arbitrary as well. But basically, if your relative motions, your relative velocity is above the fragmentation threshold, the collisions are destructive and your grains fragment. In the opposite case, your grains will stick one to the other and they will grow. And we have the mass distribution rate following these collisions. You can see it depends on the relative velocity and on the local dust density, which tells you about the number of collisions happening. And we have that formula only if we assume collisions of equal size grains. All right, so this is how dust growth works. Let me now highlight a bunch of results that have been obtained with that module. And it did not start with Fandom. Started back in time with Lyon SPH, back already in 2008. Just to highlight that this is a very old framework that has been like updated through years. And I won't talk in detail about that paper. I want to talk first about this result, which is to me more important, which is the creation of what we call self-induced dust traps. So it's basically, you have to imagine a disk, you give it some dust, initially all the same grain size, and you let that grain size evolve. So with time, your grains will grow. As they grow, they will settle and drift, right? But as they grow, the Stokes number is increasing. Stokes number increasing means number above one means radial drift velocity decreasing. So they drift, but in a slower and slower way, meaning that you form kind of a traffic jam, starting an accumulation of dust grains. If you have an accumulation of dust grains, you are promoting dust growth. And so you have this accumulation of growing dust, of Stokes number that is rising. And so at some point, your dust ends up completely decoupled from the gas and ends up stopping its radial drift. And so you have a steady accumulation of dust that is growing, and you can solve this way, the self-induced way, the problem of radial drift and losing the dust. So this is very nice. This was done with Lyon SPH, but then in 2021, this algorithm got implemented in Phantom by Arnaud Viricel. You have here a snapshot of the gas column density, and here a snapshot of the dust. And here you have several panels that show you the time evolution of the grain size as function of radius, right? And you can see, so at B, there is nothing, then you can grow some dust, right? And this hashed area is basically where fragmentation should happen. So when you reach that area, you see the grains cannot go there because otherwise they fragment, they return to their original size. The only way to overcome that limit is to form a self-induced dust trap at a given location. And you see that this self-induced dust trap allows us to solve that local fragmentation variable. So it's a very efficient process. Then some years ago, Stéphane took over and he implemented porosity in the code. Till now, we assume that the grains were full and compact. Now we can make them porous. And long story short, the porosity basically enhance dust growth, right? And you can simulate that, make that evolve in the code. And he implemented as well the snow lines. So basically the idea is that you can make the fragmentation velocity depend on space. So you can see here, for example, that inside the snow line, you have like 25 meters per second, that's the fragmentation velocity, and then outside you have 5 meters per second. This is like a way to reflect different dust properties in the disk that changes the way dust is growing. And more details on this in a letter that Jeff and Stefan submitted very recently. So these are kind of complicated plots, but basically on the left you have no snow lines, on the right you have one, and all of the particles above these colorful lines are the areas where you can form planetesimals because of the streaming instability. And this is more funny, I think. Without the snow line, the area is very small, and with the snow line, basically you can form planetesimals, trigger the streaming instability and strong clumping, which is the same, in a larger area. So the snow line should help to planetesimal formation. And then myself, so I've always been interested into binary and multiple systems. So I've applied the algorithm to this kind of systems. You can see in these panels the grain size, a function of radius again, and each panel is a different orbital configuration of the binary. So this has certain binary disks, and then you have circumstellar disks. And basically the main result is that for circumbinary disks, you cannot grow dust as much as in circumstellar disks. And the reason is because dust growth is density driven. This is what is telling you this plot. Basically, where you have density, you can grow dust. Dust can reach bigger sizes. And if you look at the dust density at the top here, you can see that the dust density in circumbinary disks is lower than in circumstellar disks. And then finally, if you look at the regions where the streaming instability can happen, can develop pretty well in circumstellar disks. But in circumbinary disks, you can see that there is no colorful area, meaning that the streaming instability cannot happen in these conditions. And this is a kind of a problem because we detect actually a lot of planets at these locations. And so you cannot explain their formation through this mechanism, basically. All right, for the last part of the talk, I'd like to talk about the possible upgrades to that dust growth module. At the moment, they all live in different universe, but I believe that we'll be able to git merge this universe into ours. So let's start with the fragmentation threshold, which is assumed to be uniform at the moment, but it's not the case in reality. So this fragmentation threshold, I've told you, depends on the grain properties. These grain properties, they depend on the local temperature in the disk. So it's great that we can put a snow line, right, to mimic that change in temperature and grain properties, but temperature is a continuous field, right? So we should be able to make that fragmentation threshold also depend on temperature, which is not the case at the moment. Fragmentation velocity depends on the dust surface material, something we can see on this little scheme. And at the moment, the dust that we have in fandom is mostly representative of silicates. We'd like to implement other species to be simulated. And finally, we are assuming that grains are compact spheres or pores, but in reality, they look more like this kind of fractal aggregates, and that changes a lot to the physics of the collisions and so the way dust is grown. Then we'd like to go beyond what we call the monodisperse framework. Monodisperse meaning that when you have collisions, it always involves two particles of the same size, and the outcome of the collision is one particle of a given size. This is very convenient because we know the analytics for that problem, and this is what is currently implemented. But in reality, you have a whole distribution of grain size, and you would like to resolve the collisions between all of these grain sizes with one collision not only giving you one output grain size, but also distribution of grain sizes. This is what is called the polydisperse framework. And so to solve that, you would have to solve these very nice equations, which are, of course, not that easy to solve. But thankfully for us, there is Maxime Lombard, who has done the job quite well with his Koala code, which is able to evolve a distribution of grain size with time. And so it's already implemented in the code, right? There is a correct file for that, and it's probably working. But Koala is not yet public yet, so we'll have to wait a bit of time. Yeah, thanks. And last part on this, the last assumption that we are doing is that the disk is Keplerian. Why? Missing something here? Yeah, let's do it well. So basically, when we compute the Stokes number, we use the Keplerian frequency, which assumes basically that your disk is Keplerian, and we need that Stokes number to compute the relative velocity. It means that also when we compute that relative velocity, we are representing the unresolved motions of these tiny dust grains, right? Remember? And we just assume that the background flow is Keplerian. But in reality, it's not at all the case. On this slide, you have printed the trajectories of particles for different systems, an isolated disk, circumbinary, and then with an external companion. And basically, when you have crossing trajectories, it means that you have collisions between those grains. You can see that on disk that is isolated, you have some collisions in the inner disk. If you have the companion in the middle, then you definitely have a bunch of collisions here. And then if you have the companion to the external regions of the disk, it becomes like a mess. And so what we would like to do is, on top of that microscopic turbulence contribution to the dust relative velocity, we'd like to add another term which takes into account the resolved turbulence, right? So all the perturbations that we can see in the disk. This is what I'm currently implementing in the code. And the method to do that is as follows. So we end up in this situation where we want to know the relative velocity of the field of particles, compared to that central particle. So what you have to do in order to do that is first you rule out the particles that will not collide or intersect trajectory with your particle of interest. Then you calculate the pairwise impact velocity, but not using the velocities that are contained in the simulations. You extrapolate those velocities to have the velocity at the impact point. And then you repeat that for all the particles in the kernel, and you average over that kernel to have a metric of the relative velocity around, well, as a continuous scale in your simulation. What is that giving? I've tested that a bit. I won't detail all the framework of this, but basically theory is a red curve. What the code is measuring is the blue one. This is very low resolution, so you have some errors at high velocity, but basically it's matching pretty nicely. So it's kind of working, but the drawback is that it's a resolution dependent method. So basically when you use it, you have to be a bit careful the resolution you use. So here you have the quantity, the relative velocity that is measured. It's a function of radius and different color are different resolutions. You can see that the very high resolution simulation with 8 million particles produce a lower estimate of the relative velocity, and that's completely inherent to the formulation of that method. Great. So this has been pushed on main. So if you would like to use it, feel free. I've listed a bunch of projects of interest for this dust growth algorithm. So if your name is here, I'm happy to have a discussion on what all the projects are. if your name is not here and you're interested into using that algorithm, feel free to talk to me as well. I'll be very happy to help. So I will just leave you with this slide, which is basically everything that I described. Thank you for your attention and taking any questions.
Thank you very much, Antoine. My question is, why is it resolution dependent? That last thing that you just showed, the highly resolution dependent. Why?
Yeah. So it's basically when you're computing the relative velocity, you use that field of particle. So if you have not many particles, you'll have like a huge distance basically between two particles. And so the velocities will be, the velocity field will be very less sample compared that if you have plenty of particles all around. And so you can imagine that if you continuously add particles and add resolution, your relative motions between neighboring particles will be lower than if you have like two very far away particles from each other. It's good.
It's good for me. Thank you. Any questions from the audience? Yes.
Antoine,
Yes.
nice work, man. So I have a question. Like in these simulations, for instance, in your work, following your framework, would you remove the star and see, for instance, in Phantom, using Phantom, if you remove the star, could you study the formation of a circumplanetary disk just to see how like dust growth happens around a planet instead of around a star? Can that be done in Phantom?
I'm definitely not the expert to answer that question. I think that's a problem of resolution here. The dust growth algorithm, it will work whatever the problem is, basically. You'd have to tune a bit some prescriptions, but can be done pretty easily, I think. But the problem is that you have to resolve the circumplanetary disk first, and then see what to do with dust growth. But I think the complicated step here is to first resolve the circumplanetary stuff, then applying dust growth to that is straightforward.
Also, it's a great comment. So we've been putting dust in binary interactions for the last 4 years with the analysis. So following the original prescriptions.
Yeah.
One thing that's always come up at the workshop is that the dust nucleation we're doing doesn't allow the dust to decouple. The dust growth we do does allow the dust to decouple, and dust nucleation and growth shouldn't. They've been developed independently, but they should really be.
A very good chat with David about this, and I'm happy to have first discussions on this. Try to tackle that issue because that shouldn't be two independent modules completely.
It's coffee time.
Yes, so coffee and cookies and fruit are outside. And there is also a